Welcome to Lesson 5-3, Non-Uniform Circular Motion. The objectives of this lesson are going to be to describe the difference between uniform circular motion and non-uniform circular motion, as well as calculate the tangential and centripetal components to an object that has non-uniform circular motion. So, when discussing circular motion in general, whether it be uniform or non-uniform, we really want to consider only two directions, centripetal and tangential. And you almost want to consider them like as if they're the x and y direction. Now, centripetal is of course a direction, and it is the direction pointing towards the center at any point on a circle, or any point on an object's circular motion. Tangential is referring to the direction that always points tangentially outward from a circle in a linear path. In this case, you'd see that this would be true about three different tangential directions if we're moving in a counterclockwise direction. When an object is moving in a circle at a constant speed, the net force acting on it is only centripetal. However, if the net force isn't exactly towards the center like you see here, but rather at some angle with respect to the radius, at some angle here, we can say that the force vector can be broken up into its centripetal and its tangential components. The centripetal component is the part of the force directed towards the center of the circle, as you can see correct here. It's pointing exactly towards the center of the circle, and that's why we call it the centripetal component. It's still the only thing responsible for making the object continue its circular motion. So nothing has changed about the centripetal force. It's still going to be expressed by the expression mass times velocity squared over r, and that's tangential velocity over the radius of the circular motion. And the acceleration component that is centripetal is then just without the mass, tangential velocity squared over the radius of the circular path. Nothing changes from the uniform circular motion to the non-uniform circular motion when it comes to centripetal component to force or centripetal component to acceleration. The only difference is that now we do have a non-zero tangential component. This is part of the force that causes the velocity, the tangential velocity of our object in circular motion to change, and it works just like one-dimensional kinematics, So what I'm saying is that the force tangential, the tangential component of force, is just mass times average acceleration. So this is Newton's second law, but for acceleration, we've plugged in the definition of average acceleration, which is delta v over delta t, right? And then of course, the tangential component to acceleration is just that definition for average acceleration, where v is the magnitude of the object's linear velocity. So the tangential acceleration is just the rate of change of the object's linear speed. Because of this, when you swing a ball on a string, initially you have to give it some push, tangential acceleration, to get it moving. As you do this, by pulling the string, the ball starts its circular motion, and then the centripetal force from the tension in the string can keep it in a circular path. The two accelerations caused by the two components of force will point in the same directions as their respective force vectors. We know this because F equals ma, Newton's second law, is just a scalar multiple, so acceleration always points in the same direction as the force. So what I'm saying is that a free body diagram breaking up the force into its components will look very similar to a free body diagram breaking up the acceleration into its components, As such, the components of acceleration are always perpendicular, right? So when we give the components themselves, we can always use the Pythagorean theorem to find the resultant acceleration vector. In other words, this acceleration resultant vector that's pointing in truth where it's supposed to be pointing can always just be equal to the square root of the square of the tangential component plus the square of the centripetal component. All right, let's consider a race car starts from rest in the pit area and accelerates at a uniform rate to a speed of 35 meters per second in 11 seconds, moving in a circular track of radius 500 meters, assuming the constant tangential acceleration. That's beautiful that we get to assume constant tangential acceleration because at some point we can just use the big five kinematics. All right. It wants us to find the tangential acceleration, find the radial acceleration at the instant when the speed is equal to 15 meters per second. So part A is just asks us to find the tangential acceleration. And it tells us that in this scenario, we have constant acceleration, so the acceleration should be the same anywhere on the circular path. So if we are dealing with some circular motion, okay, and we have some car accelerating from rest in a counterclockwise path, I'm just assuming a counterclockwise path. You could definitely set this up to where it was accelerating in a clockwise path. But it's telling us that at some point, okay, given 11 seconds passes, then we have some final velocity that's equal to 35 meters per second. Okay. So we know that we're also starting from rest, so we have the initial velocity to be 0 meters per second. Okay. Now, given the fact that we have constant acceleration, and the fact that we can treat the tangential component to acceleration and force as one-dimensional kinematics and dynamics, then we can use one of the big 5 kinematic equations to find the tangential acceleration given these 3 components of the motion. All right. That said, the equation that comes to mind is the fact that v final is equal to the initial velocity plus acceleration times time. We are given final, initial, and time. All we need to do is solve for the missing piece, acceleration. I'm going to go ahead and plug in 35 meters per second for final velocity. The initial velocity is 0 because our car starts from rest. And I'm going to set this equal to a times 11 seconds. 11 seconds. If I divide both sides by 11 seconds, then I get roughly 3.18 meters per second squared. That is a unit of acceleration. So I can say that my tangential acceleration, a sub 10, is equal to 3.18 meters per second squared. And that's the answer to A. But what about B, the radial acceleration? At the instant when the velocity is 15 meters per second. Now, it's important to point out here that when it's asking for radial acceleration or centripetal acceleration, those are the same thing, by the way, then it's going to indicate at a specific point, because the fact that centripetal acceleration depends on tangential velocity. When tangential velocity is changing, so too must the centripetal acceleration. So it's going to point out either at a specific time or at a specific velocity to plug in for tangential velocity, because, as I said, centripetal acceleration is equal to, and always equal to, v squared over r, where v is that tangential velocity. So that's why it's telling us to plug in 15 meters per second for v. And of course, earlier in the question, it tells us the radius of the circular motion is 500 meters. So we have everything we need to plug straight in here. 15 meters per second, quantity squared, over 500 meters. Now I'm going to square 15 in my calculator really quick. And that should give me 225 meters squared per second squared over 500 meters. Now that 500 meters is going to cancel out one of the meters on top, and it's going to leave us with an acceleration, which is meters per second squared. So I just need to take 225 and divide it by 500. This gives me a centripetal acceleration of 0.45 meters per second squared. And if I were to take this information, and of course if I were to take this information, these 2 components of acceleration, which I'll box really quickly, okay, and if I was to draw a free body diagram somewhere here, and I was assuming that the motion of the car was in the counterclockwise direction, then I would have a rather long acceleration vector here, which should be tangent to the circle. So let me adjust the position a little bit. Okay. And then a rather short acceleration, centripetal acceleration vector, since the magnitude of the centripetal acceleration is significantly smaller than the magnitude of tangential acceleration. All right. So that would mean that the resultant acceleration is actually something like this. And we want it to be the diagonal of a rectangle between the 2 components. All right, guys. There are extra practice problems tied to this lesson linked below. There also is a solutions video to each one of those practice problems. Happy studying. I'll see you guys in the next one.